Okay, hello everyone. It has been a long time. So what happened is we learned about the rate law. If we are given a specific chemical reaction, something like this, A plus BB equals C product, and we know that the rate must be proportional to A to some kind of order, B to some times of order, and the K is called the rate of constant, the order of reaction. This must be determined experimentally. Otherwise, by default, we theoretically assume that the coefficient is going to be the order. Okay, what do we mean by order? So, zero order, constant, K, first order, second order, see the power over here, okay? And if we double A here, this one is also going to double, this one have no effect, and this one is going to be quadruple. Okay, the overall order of the reaction is all of the reactant. You just add their order together. For example, there's only one reactant. The order is 1, you just plus 1. There's only one reactant, 2, you take 2. There's 2 reactant, you have 2 plus 1, 3. This one I don't know what the hell is going on. So 1 and 2. Here we plus 3. And what is the order with respect to 1, 1, 2? With respect to each reactant, what is the overall order of the reaction? So 1, 1, 2. That's 1 plus 1, 1 plus 2. That's 4. And rate constant. So the rate constant is going to be the thing that's balancing out this thing and this thing. And the bigger of this whole thing is, if the K is bigger, that makes this overall this thing becomes bigger, and this going to be faster. The speed of the reaction is going to get faster. And yeah, sometimes if you get a negative order, that means the more you add a substance, the slower it is. And yeah, just need to mention that the unit of the K is going to be depending on the reactant and the order. The rate, we know that it is always something like moles per liter second, and the reactant is like moles per liter, and obviously K is going to divide by an S, and you need to balance it out, cancel out the extra moles per liters, and to get liter per mole here. No. You need to cancel out the extra moles and over liters, and get some kind of I don't know. To get by the end you should get moles per liter per second. Like this is an example. And yeah, from experimental data, so we have a 3 set of data, and we are given 2 different reactant numbers and the overall react rate of the experiment. What we need to do is just pretend this is like a system of equation with 3 different variables, and each equation is in form of this. And what we need to do is we first cancel out the K, right? And then we can try to manipulate M and N and just try to cancel out one of them by multiply this whole thing by something by the things that this M and this M is off. and then we will be only left with n, and use logarithmetic we can get the value of n. Just use your calculator, alright? And it should not be too hard. Let's try this one. Okay, let me get my pencil first. Okay, for example, this one. The first one can be written as first check if the units are the same. Like, there's some tricks here. This one is times 10 to the power of 3. It's kind of tricky. Ha! The first one is 10 equals to K 0.1 m 0.1 n, and the second one is 20 equals to K 0.2 m 0.1 n. The third one is 30 K 0.3 m 0.1 n. Okay, so I don't think we even need the fourth one, because in order to solve for 3 variables in a system of equations, you only need 3 equations. That's it. How many variables are there, and that's how many variables you need. Unless the equation is kind of competitive and you get no useful information from the other one, okay? And first we're gonna try to cancel out the n. So 1 divided by 2, you see. And we get 1 over 2 on the left side, and we cancel out the k and cancel out the 0.1 n. And we get 1 over 2 m. M equals to 1. Great. Awesome. And now we can substitute the 1 into m. So 0.1 multiplied by 10 to this side. K 0.1 n. 0.2. That's also going to be 100, huh? Actually, oh, you know what? The third one is kind of useless. We should take the fourth one because it's repetitive. Okay, so far I use number 1 and number 2. Number 4, I gonna 0.4 n. Okay, and I substitute m here. M equals to 1 and 0.4 400. So the fourth one, once you substitute m equals to 1, 0.4, you divide that by 0.4, and that's going to be 400. K 0.4 n. Okay, and then you're gonna also cancel out the k here. 1 divided by 4, that's going to be the k cancel out, 100 cancel out, 1 over 4, and this is also 1 over 4, and n, obviously n equals to 1, and you substitute both n and m into any one of those equations. For example, this one, 10 equals to 0.1 times 0.1, that's equals to 0.01, and you multiply both sides by 100, you're gonna get 1000, k equals to 1000, and we get the rate equals to k equals to A1 B1. Okay, that's how we get the answer. And let's also talk about factors that affect the rate of reactions. There are so many factors such as temperature, surface area, concentration, and the phase of the reaction, and blah 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 blah, blah, quite a lot. Okay, for example, this one, gold and copper, they are both used in jewelry, but one is turn green, but copper turns green over time. Although they are both metals and they belong to the same family, but we know that each chemical, they kind of just have different chemical nature, you know. And milk keep in a refrigerator keeps for a week and more, but milk left over in the counter will quickly turn sour. That's the temperature. You know, the faster the temperature, the faster the reaction. Papain is a food additive that sometimes be added to make it even more tender. So it's probably a catalyst because it's never been consumed. The dust in the grind silos has been known to explode, whereas kernels of grains are almost non-flammable. Yeah, I think this is the surface area, and the vinegars is safe to add to the food and consumption, and the pure acetic acid will burn the skin and the contact. So this is concentration. Vinegar is not that condensed, but the pure acetic acid is very dangerous. So reaction mechanism is a theoretical explanation why some reactions are fast and some are slow. And it is depending on each kind of different factors. And we are just trying to break a very overall chemical reaction into different steps. And for each step, for it to happen, we must have sufficient energy and the correct orientation. For example, we have A, B, C, D here. For example, we want to, originally AB are bound, DC are bound, we want to form AD bond, BC bond. See, it has to be having the correct orientation and it has sufficient energy. However, like this one, it's not the correct orientation, or maybe it's just not having enough energy. It's not going to happen. And according to and the minimum energy that required is called activation energy, or it contains a certain minimum energy threshold. And why does the concentration of reactions lead to more collisions? Because it leads to faster reactions and more collision and more chance for that to happening. And the temperature of the reactants, it also increase the chance the speed of the overall reaction, because it helps more molecules to have to get above the activation energy and increase the chance of valid collision. And this question, they are in the same temperature, which means they all have the same average potential energy. And the EA1 is greater than EA2. The activation energy of this one is lower. That means it's easier for the molecules to get above this threshold and more valid collision. So this one should be faster. And the Maxwell Boltzmann distribution curve states that it gives us a very good example of how much percent of molecules a certain amount of kinetic energy. Once the temperature gets higher, this peak is going to slightly lower and shift into the right. Thus, increase the number of molecules that possess enough energy. But the temperature is not going to affect the activation energy. It only changes the number of molecules that has certain kinetic energy shift the graph to the right, but it didn't really move this bar here. And yeah, so speed. So one thing to keep in mind is that some of the molecules, they are heavier and some are lighter, and the temperature guarantees that they have the same energy, but we know that the heavier molecules is going to be harder to move and the lighter is easier to move. Therefore, the lighter ones move faster and the heavier one moves slower. Like H2 is very light and O2 is very heavy, so it should be to the right and O2 should be on the left. And the catalyst. So what catalysts do is it kind of lower the activation energy bar here. Well, how you gonna imagine this is the catalyst provides an alternating path for the reaction to happen. For example, the original one requires very high activation energy. So the activation energy is here. You see the reactant here. The highest peak is going to be the activated complex, and the distance of this is going to be the activation energy, and this is going to be the new activated complex. Therefore, this is the new activation energy threshold. Therefore, see, this one is lower, which means it's more easy for the valid reaction to happen. And for the reverse one, also you just need to reverse the graph, and this is going to be the energy activation. Okay, see? But for the enthalpy, we only care about the difference of the reactants and the products and how much they're off by. We didn't really care about their activation energy and the actual curve, the path, okay? And let's talk about reaction mechanism. So we just breaking down the reaction into different multiple steps, and by theory, some of them are slower, some of them are faster, and the overall reaction cannot be faster than the slower one. So the determinant step is going to be the slowest chemical reaction. And here is this very important. The theoretically obtained rate law must be identical to the derived rate law. So we are just assuming that the coefficient is going to be our order of the reactants, okay? And it must be agreeing to the actual experimental data. So intermediate is anything that's being formed first and then being consumed. And the catalyst is anything that's on the left side. First they are being consumed, then later being reproduced, getting out of there, and didn't really consumed in the process. And all we need to know is that okay, let's look at this question actually here. So we're gonna assume that the reversing reactions is equals to like the direct reaction. Here we take the slowest step here, N2O2 H2, just like the rate law, but we know that we cannot have any intermediate inside our rate law. So we substitute this N2O2 with NO because we assume that here, okay, the direct reaction of the first one is equals to some kind of K to the NO to the power of 2. And the reversing one is rate equals to k some other k, okay, equals to N2O2, and we are assuming that those two are equal, so k equals to NO square and k N2O2. We assume they are equal, and we substitute N2O2 equals to k, the new k here to the square, because this is some kind of constant, so we just replace it as k, okay? It doesn't matter, so n2 square, we replace that with no square, okay? Here, this is just some kind of k, we just write it k, okay? And when you are constructing some kind of reaction, you only need to care about first, the slowest reaction determine the step. So 1 and 1, that's going to be the order, right? And 1, it match the first step, and the overall reaction, it cancel out and get exactly the overall reaction. So yeah, that's how you construct it. And there are more example over here. And when you are reading the potential energy diagram, you're gonna count how many like curve it has. For example, this one, it has 1, 2, and 3. Therefore, there are 3 different reactions. And the overall, you just need to care about the beginning and the end. So this one is higher, this one is lower, so it's exothermic. And in order to find the rate determining step, so we need to know that for each different reactions, which one of them have like the greatest distance from the reactivated complex to the beginning of the reaction. See, this one is higher than this. This one is the highest because see, this one is this high, and this one is this height, and this one is the highest, and this one is the highest. See, this one is kind of small here. This one is the highest. So see, and that's pretty much for today, and thank you for watching.